Let's get into thermochemistry. And in thermochemistry, let's try and understand what do we mean by enthalpy. Now, in case of enthalpy, enthalpy is energy required for making a molecule. Now, enthalpy, it could be delta H0, that is standard bond enthalpy, or delta FH0, that is bond formation enthalpy. This obviously is for bond breaking enthalpy, and this is for bond formation or bond making enthalpy. Alright, now let's try and understand in depth. Suppose the reaction that we are conducting is CHCl3, methyl chloride gas, chlorine gas, giving you dichloromethane, CH2Cl2 gas, and HCl. Alright, this is the reaction. Now let's calculate enthalpies, individual enthalpies. We have been given the enthalpies. CH is each CH bond breaking. Mind you, what they have given over here is del H0. Del H0 is bond breaking enthalpy. Alright. Now, so CH bond breaking, each bond breaking requires 414 kilojoule per mole. If breaking requires 414 kilojoule per mole, then making obviously would be negative 414 kilojoule per mole. Alright, so it goes that way. Forward, if a forward reaction gives out energy, then backward reaction would be taking in energy. Alright, so it's always like that. So similarly here also, when we talk about ClCl, single bond of ClCl breaking requires 243, HCl requires 431, CCl requires 330 kilojoule per mole. Alright, now when we pick up CH3Cl, we know it has got 3 CHs, 1, 2, 3 CHs and 1 Cl. So 3 CH plus 1 CCl, 1 CCl. So we just pick up from there. We know it is 414 into 3 plus 1 of CCl. We pick it up from there, CCl 330. So it is. So when we add up, what we end up with is 1572 kilojoule per mole. Now this is the enthalpy that this molecule possesses. Alright. So that is what is del H0 for this molecule. Now if we look in for Cl2, ClCl, which already is given over here, it is 243 kilojoule per mole. So that's the enthalpy that it possesses. Then again dichloromethane. For dichloromethane also similarly we do. What we have is 2 CHS and 2 CCl, 2 CCl, CCl. So that's what we did, and ultimately the energy that it possesses is 1488 kilojoule per mole, and HCl is 431 kilojoule per mole, which already is given. Now what do is we place all those values, all those enthalpies that we calculated under individual molecules. So for CHCl3 we calculated it to be 1572, for Cl2 we calculated it to be 243, for dichloromethane CH2Cl2 we calculated this much and this. So it's all jotted down. So we sum it up. On summing up, we find that enthalpy of reactant is 1815. Mind you, it is not formation, right? Keep that in mind, because that's going to come later into our use. So it is this, and for product enthalpy is, so I hope you get the idea about enthalpy. How is it calculated and how does every molecule has its own enthalpy. Alright, so here the reactant is this, here the product is this. Now, okay guys, now comes the crucial part. I have been talking about delta FH and delta H, that is delta formation enthalpy and delta enthalpy. Delta formation of enthalpy is energy required, and 0 stands for standard. Delta F enthalpy stands for energy required for formation of that compound or that bond, and delta H is the breaking of that bond. Obviously one has to be positive, other has to be negative. Now let's check out how does the sign change with application of these. What we have done is we have found out these values for reactant and for product. Now for del F, if we are provided in data, if we are provided with del F enthalpy, standard enthalpy, then we use summation of product minus summation of reactants. Then we use summation of products minus summation of reactants. But if we have been provided with del H0, then we use summation of reactants minus summation of products. So what have we been given? Though I have applied both, just to show you the difference. What have we been provided with? We have been provided with del H0. Alright, so our formula would be summation of reactants minus summation of products. So when we do this, the value that we get is minus 104 kilojoule per mole. Now when it is minus 104 kilojoule per mole, negative, whenever it is negative, that itself means it liberates heat. This reaction would be liberating heat. Now let's understand what happens if we, by mistake, we use this formula. Alright, that is assuming that they have provided us with delta formation enthalpy. So this is what happens. We did this here and we got the same value. Obviously it's a difference, so we would get same value, but it is positive here. That itself means that here it would be absorbing heat. So it becomes so very crucial for us to understand what have we been provided with, del F H0 or delta F H0 or delta H0. Accordingly, we have got to use the formulae. All right. Now, I would like to also introduce a term. Now, whenever it is negative, whenever the enthalpy of reaction is negative, we call it as exothermic reaction. All right. And whenever it is positive, we call it as endothermic reaction. So the reaction which we chose is exothermic reaction. That is, it would give out heat, it would release heat. So see, if we use the wrong formula, so please, this is just to make you aware about whenever you are tackling any numericals of any competitive exam or anywhere, you have got to be very clear about what has been provided and which formula you are supposed to use. All right, so next mission is, now let's graphically understand what do we mean by exothermic and endothermic.